Howdy. This is the video that introduces the experiment synthesis of aspirin. We're doing in CHEM111L. So aspirin was developed by the Bayer company. That's why we have Bayer aspirin. Obviously, a lot of other people make it now, but Bayer was the first company to do that. They're a German company. Aspirin is also known as acetyl salicylic acid. So acetyl salicylic acid is the chemical name for aspirin. The structure of aspirin has a 6-membered carbon ring system as its core, and in that ring are these alternating single and double bonds. Okay, off of a couple of the carbons are some other groups. There's the acetyl group off of that carbon, and then off of this top carbon, doesn't really matter, it's just got to be one away from the other one, is carboxylic acid group, and that's just a C-double bond OH group. That's an organic acid group. All right. Off of these carbons, because we know carbons have 4 bonds to them to follow the octet rule. Off of each of the carbons in that ring that doesn't have something else off of it, we're going to put a hydrogen. Okay, and then also we need to put a pair of lone pairs on each oxygen to give them, each oxygen, an octet. Okay, so that's acetyl salicylic acid. That's what we're going to make today. And that's aspirin. That's the active ingredient in aspirin. A few things we need to know about aspirin. It obviously is a pain reliever, and a pain reliever is known as an analgesic. Okay, so aspirin is an analgesic. It reduces pain. It's also an antipyretic. An antipyretic is a fever reducer. So if you've got a fever, you can take aspirin to help reduce the fever. It's also anti-inflammatory. Meaning that it reduces inflammation. All right, so reduces inflammation. Okay. Also, individuals that have heart disease, high blood pressure, have had a heart attack, will often take baby aspirin to help reduce the chance of having another one. All right, so these are the common uses of aspirin. The one main detractor from aspirin is that this acid group up here causes a lot of people to have stomach issues. It causes an upset stomach or discomfort in the stomach. So there are ways to get around that. They'll buffer the aspirin so it doesn't dissolve in the stomach, but will dissolve in the intestines and still get absorbed. But that is definitely one of the main detractors from aspirin, is the fact that it does cause issues with some people's stomachs. All right, so to synthesize aspirin, we're going to start with salicylic acid. So let me draw salicylic acid here for you. Salicylic acid has that kind of same core 6-membered carbon ring that aspirin does. It's got the carboxylic acid group on the top here, but it also doesn't have the acetyl group. It's got this OH group on the side of it. Again, we have all these hydrogens to complete the octets around the carbons, and then obviously we got to put our lone pairs on our 3 oxygens to give them octets. Okay, so that's salicylic acid. And salicylic acid actually works as a anti-inflammatory, antipyretic, analgesic. It does the same thing except as aspirin, except it's actually much worse for your stomach than aspirin is. Okay, so as we said before, that aspirin has this acid group up here that causes stomach issues. In addition to that, salicylic acid has this what's known as a phenolic group. And a phenolic group is this ring system that's got the alternating double bonds and this OH off of it. An OH group is an alcohol group. And both of these parts of the salicylic acid cause upset stomach. It cause issues with stomach. So the Bayer company in Germany, I want to say just before the turn of the century to the 1900s, so late 1800s, decided that they could improve on salicylic acid, so they replaced this with the acetyl group to reduce the issues that salicylic acid has in people's stomachs. So let's go through the synthesis here real quick and what we're going to do today. So we're going to start with salicylic acid. So we'll start with our salicylic acid, which is that one. Throwing everything on here to make everything have an octet. Okay, so that's our salicylic acid. Oop, don't need that part. Let's erase that, because I can. Okay, so going back to our pen here, that's our salicylic acid. And for later purposes, we're going to need that salicylic acid has a molecular weight of 138.2 grams per mole. So when we're calculating theoretical yield and things like that. Okay, we're going to react that with what's known as acetic anhydride. And acetic anhydride looks like this. That's a bond. That's an H. That's an H. That's an O. So put our lone pairs on these guys. And then we basically have a mirror on the other, mirror image on the other side of acetic anhydride. That needs to be a hydrogen, not a carbon. So we're going to react the salicylic acid with acetic anhydride, and this acetyl group, the C double bond O CH3, is going to attach to the oxygen where the hydrogen is, right? And that's going to form our acetylsalicylic acid, aspirin. Okay, so pen right here, C, 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 and remember acid group up here still, which still causes some stomach issues, but a lot less. And now off of this, we have our acetyl group, which is why it's called acetylsalicylic acid. Putting our lone pairs everywhere we need on our oxygens, and then we got to add our hydrogens to the ring. So it's a hydrogen, it's a hydrogen, it's a hydrogen. So now we have a good Lewis structure. The other product here is water. That's left over from the two hydrogens leaving the salicylic acids and the leftover oxygen here. So this is acetic anhydride. And acetic anhydride has a molar mass of 102.1 grams per mole in case we need it later. This is aspirin, and that has a molar mass of 180.2 grams per mole because we're going to need that later. And obviously that's water, and water has a molar mass of 18.0 grams per mole. All right. If we balance this, we see that we're going to start with two salicylic acids. We're going to react with one acetic anhydride, and we're going to form two aspirins and one water molecule. All right, so that's balanced. And a couple of other things to note here. We're going to start with about 2 grams of salicylic acid. We're going to add 5 milliliters of acetic anhydride, and then we'll determine how much aspirin we make. In addition to this, we're going to add a little bit of H2SO4, sulfuric acid. Okay, and I write that above the arrow because it's not part of the reactants and it's not part of the products. It's actually a catalyst. So let's discuss catalysts for a minute. All right. So a catalyst is simply a compound or molecule. So I'm going to write it as a compound that is added to a reaction to increase the rate of the reaction. And what that simply means is we're going to add the catalyst to the reaction so that our reactants get to products faster. So if we do this reaction without without sulfuric acid, it takes a lot longer to make aspirin from our reactants. Right? That sulfuric acid is going to help push this to reactants to products a lot faster. Right? So one thing to notice is that catalysts are not used up in the reaction, meaning that the amount of sulfuric acid that we start with, we end with. So they're not part of the reaction, or they're not part of the reactants or products, right? So they're not catalysts are not used up or depleted, I guess we could say, during the reaction. That's why they're typically written above the arrow, right? They're not part of the reactants, they're not part of the products. So usually those additional things like heat, when we applied a lot of heat, when we did baking soda the other week, where we put the delta, that triangle above the arrow, saying that, hey, to get to the products, we got to apply heat. Same type of thing here. If we add a catalyst, a lot of times we'll write it above the arrow just to show that we've added a catalyst to increase the rate of the reaction. So that's about it in this reaction. We're going to set up in a beaker, a flask with our salicylic acid. We're going to add our acetic anhydride, slightly add the acetic anhydride, add 5 drops of sulfuric acid. We're going to slightly heat the system to get to products. And then we're going to collect our products using filtration, very much like we did with the calcium phosphate, except we're going to use vacuum filtration or suction filtration, whichever way you want to call it. And that should get us product a lot faster than we did with the calcium phosphate. That gravity filtration takes a lot longer than vacuum filtration. So we're going to set this up to go a little bit faster with the sulfuric acid and then we're going to filter faster with vacuum filtration. See you in the lab. Alright, so the last thing we should discuss is the calculations that we're doing here. The main calculation is going to be the theoretical yield of the aspirin from the salicylic acid that we start with, and then you're going to do a percent yield. So these are very similar to what you've done the past 2 weeks with the baking soda and the calcium phosphate. So in this reaction, we're reacting salicylic acid with acetic anhydride. Salicylic acid is the limiting reactant, so it will be the mass that we're going to use to do our calculation of our theoretical yield. Right, so we need to calculate the theoretical yield of aspirin, and we're starting with our limiting reactant, which was salicylic acid. It tells us we're going to use about 2 grams of salicylic acid. So we're going to start with that. Alright, and if we got that, and that would be in grams, so we need to convert that to moles. And we were told that 1 mole of salicylic acid has a mass of 138.2 grams. So we use that, I'm going to write that as salicylic acid, SA. So we're going to use the molar mass of salicylic acid to convert to moles of salicylic acid. And then in our balanced reaction, we saw that 2 moles of salicylic acid produces 2 moles of aspirin. So that will give us moles of aspirin, right? So our mass of salicylic acid converts to moles of salicylic acid. And then we use the balanced reaction to go to where we want to go, and in this case it's aspirin. So we now have moles of aspirin. Theoretical yield is typically done in grams, so we're going to convert to grams. So to convert from moles to grams, we need the molar mass. And the molar mass of aspirin is 180.2. So we'll do 180.2 grams of aspirin is 1 mole of aspirin. And that will give us the mass of aspirin that we should produce from the salicylic acid that we started with. Okay, so that's going to be our theoretical yield. You're also going to do a percent yield, and if you remember, percent yield is the actual yield, so the amount of aspirin that we collect in lab divided by the theoretical yield, which is what we would just calculated, times 100% to get us to percents, and that'll give us the percent yield. So just like you've done the past 2 weeks, we're using the same type of calculations to calculate theoretical yield and percent yield. And that's all you got to do. Hey, we're in our favorite place one last time. Today we're going to do the synthesis of aspirin, the last experiment for CHEM111. It's a pretty simple experiment. We're going to react salicylic acid with acetic anhydride in the presence of a catalyst to produce aspirin and water. We will heat it to make the reaction go a little bit faster. And then we let it cool, put it on ice to get as many crystals as we can, and then we'll use filtration just like we did with calcium phosphate, except today we're going to use suction or vacuum filtration. It's a lot faster. The crystals that aspirin makes are really nice crystals, so they are really amenable to vacuum filtration. After we collect our product, we're going to test its purity, because purity is really important. You want a good pure product. And then I'll show you what to do with all the material and the waste, and we'll be done. Let's get things going. Alright, here we have our two reactants, salicylic acid and acetic anhydride. We have an Erlenmeyer flask, 50 milliliters, that we're going to put the salicylic acid in to do the reaction. And because we need 5 milliliters of acetic anhydride, we have the graduated cylinder that we'll use to measure the 5 milliliters. Okay. Next to that, we have a hot plate, and then a hot plate is going to let us heat our reaction very briefly, just to get the reaction going a little bit quicker. But we're not going to heat it very much, because if you heat it too much, it burns your sample. Okay, behind us here, after we get crystals, we're going to put the beaker in an ice bath, and that's an ice bath. It's got some ice and some water in it, and that's simply going to cool down everything and produce as many crystals as we possibly can of aspirin. Okay. We have our filtering apparatus right there. We have a ring stand. You can see we've got a sidearm flask there that we'll connect the vacuum to. The box contains filter paper, so we'll weigh a filter paper just like we did with calcium phosphate. The funnel there is to put the filter paper in. So we'll show how to set that all up when we get to that point. This is going to be a comparison so we can determine how pure our product is. And then two other reactants, or two other chemicals we're going to need are in the hood. We have the sulfuric acid right there. It's concentrated sulfuric acid. It's really corrosive, so that's why it's in the hood. And next to that is the iron 3 chloride, which is also in acidic solution. So we've got it in the hood. We're going to use that to test the purity of our product. One last thing about our reactants is that acetic anhydride is also very corrosive. So we're going to take care not to get that on our hands or clothes or anything like that. All right, because it'll eat right through it. All right, so next thing we need to do is weigh about 2 grams of salicylic acid. So let's go over to the balance. So here at the balance, we have our flask, we have our salicylic acid. We need about 2 grams of this. And I'm going to do this by difference again. I'm going to weigh the flask, and then we will add 2 grams of salicylic acid to it and get the total mass of the two. So the flask has a mass of 31.966 grams. That means we're going to need about 34 grams total, a little bit under 34 grams total to get 2 grams of salicylic acid in there. So let's get rid of this. $34, went over a little bit. Let's take just a little bit out. Nice, a little bit over 2, but that's fine. So close that. So the mass of our flask and the salicylic acid is 33.997 grams. Okay, now we're going to take and add the acetic anhydride. Alright, so here we are. We've got acetic anhydride, and we need to add 5 milliliters of this to and dump it into our salicylic acid. So I've got a graduated cylinder here. I'm simply going to add, to get 5 milliliters. It's a little bit over 2. Just a little bit more. Alright, so we're adding enough acetic anhydride that it's actually the excess reactant, so that our limiting reactant will be the salicylic acid. So this is about 5 milliliters. It's right, the meniscus is right at the 5 milliliter line. So we're going to add that to our acetic anhydride, excuse me, to our salicylic acid, and that should start to dissolve. And now we're going to go over to the hood and add 5 drops of sulfuric acid. So we're at the hood now, because that's where the sulfuric acid is. Sulfuric acid is very corrosive, and this is concentrated, so this is really, really corrosive. So we're going to not get any on us. So we just need to add 5 drops. 5. There's 5 drops. And we're going to swirl it around a little bit. And basically what we're going to do is take this over to the our hot plate and heat it just enough to get it all to dissolve. Okay, so we're at the hot plate. I've turned it on a little bit earlier just to let it warm up a little bit. It's just warm to the touch, and that's kind of what I want. I'm just going to put this on there just to start getting things to dissolve better. Swirl it around. I don't want to leave it on here too long. I'll start getting the product to kind of burn. So you can see already most of the crystals are dissolved, and I'm probably starting to form some aspirin. And aspirin is not soluble in this. We should start seeing crystals at some point. So I'm just going to let it heat a little bit longer and swirl it around a little bit here. Just trying to get all the crystals off the side. Alright, give it a few more seconds here, but that's about all we need. Just wanted to get all the salicylic acid to dissolve. See how everything's dissolved. So now I'm just going to let it cool for a little bit, and then we're going to put it in the ice bath. Alright, so we're over by the ice bath. I want to see if we can see. So I'm zooming in on the bottom of our container, and those little white dots are crystals starting to form of the aspirin. So I'm going to put that whole thing now in the ice bath. So there's our ice bath. I'm just going to put it in the ice bath. And just let it cool for the time being. You can see it's just sitting in some ice water there, and we should get a lot more crystals as it cools off. Pull it back out. So we're just going to let it sit in there for 10-15 minutes, and we'll come back and check on it. Alright, so we're back at the ice bath here. I'm going to pull this out to show you what we've got. So you can see all of the white solid in the bottom is actually our precipitate, our aspirin. Okay, so what we need to do now is says to add 20 milliliters of water. So I am going to put a beaker of water in the ice bath. So I want to cool down that that water. I'm going to let that cool, and then we will add 20 milliliters of that cold water to our sample. While that water is cooling, I'm actually going to throw our flask back in the ice bath also to keep everything cold. Right, so while that's sitting in the ice bath and we're letting that cool a little bit, I'm going to set up the filtration. We're going to put a clamp here. I'm just going to turn it around this way actually to make things a little easier. And that clamp is going to hold our sidearm flask. And you can see the sidearm flask has a side arm to it, and that's where we're going to attach the vacuum. So I'm going to put that in our clamp just to hold it steady while we're doing the filtering, because we don't want everything to spill. Okay, so I've got the sidearm attached to our ring stand, just to keep it steady. And then I've got the tube. I'm going to attach the tube to the sidearm. And then this goes on the sidearm of the water faucet. So what's going to happen is that when we turn on the water, as the water flows past this sidearm, it pulls the air into it. So it's going to cause a vacuum to occur over here. Our filtering apparatus, our filter funnel is just going to go on the top here. It's got a little rubber adapter to make a nice seal between the filter and the sidearm flask. And the last thing we're going to need to do is weigh some filter paper. So we'll do that next. Okay, so we're at the balance. We need to get the mass of a piece of filter paper. We're going to grab one of these. They're a bit smaller than the ones we use for the calcium phosphate. Just throw that on there. So that filter paper has a mass of 0.221 grams. So now we can go filter our product. Okay, so we're back here. I'm going to zoom in on our product here a little bit. So we have our product, and it says to add 20 milliliters of distilled water to it. And I've chilled the distilled water right here. And I've got a 25 milliliter graduated cylinder. So I'm just going to add about 20 milliliters of this ice cold water to it. So it's about 20 milliliters. And now I'm going to add that to our aspirin, or our product. I'm going to swirl it around a little bit to see if I can break that up. Okay, I'm going to grab a stir bar or stir rod to try to break that up in there, and then we're going to filter it. Okay, so now we've got our aspirin, and it tells us to add 20 milliliters of water. I've chilled the water in the ice bath, so it's cold. So I'm going to add 20 milliliters of that to this graduated cylinder, and then I'm going to add that to our aspirin precipitate. And what that's going to do is just give us a chance to break up the aspirin a little bit. Aspirin is not very soluble in water at all, so we shouldn't see much of that dissolving. Okay, so now we've got our aspirin broken up, ready to filter. I've got our filter paper here. Bring this out a little bit. I've got our filter paper here. It's just going to go in the filter funnel, and then, like we did with the calcium phosphate, I'm going to turn on the vacuum, so that will cause the vacuum to start pulling that filter down and whatever's on the top down. I'm going to add some water to get that filter paper to lay down nice and flat, and you can see the vacuum's pulled the water through. So we're good. So we can now dump our aspirin solution in there. So we can see there's some aspirin still in the flask, so I'm going to add a little bit more cold water and swirl it around a bit. I'm going to do this a couple times to see if we can get most of the aspirin out of the flask. Okay, still got a bit in there. I'm going to add just a little bit more cold water and swirl it around. See if we can get some more out, and it did. It's a little bit left, definitely some on the sides, so I'm going to add a little bit more. So we get most of that. Do that one more time here. And we're pretty good. Dump that in. The flask is pretty clear of solid. We're just going to let the vacuum work a little bit. I'm going to pour a little bit of cold water on the top here just to rinse the aspirin off a little bit. Make sure everything that isn't aspirin is kind of washed through. We can see there's a little bit of solid that got through. Must have been really fine particles. But most of our aspirin is up top. So we're going to let that pull vacuum a little bit to try to get as much liquid out of there as we can. Okay, give that a couple minutes, and then we're going to come back and we'll take the filter out and put it on a watch glass. Alright, so I'm here at the balance because after doing the filtering, I've decided that I want to put the filter on a watch glass to let it dry overnight. So I want to weigh the watch glass so we can just weigh the whole thing tomorrow with the aspirin on it. So that watch glass has a mass of, let's stop shaking there for a minute, 49.218 grams. So now we can take our filter with the aspirin on it and put it on the watch glass. Alright, that looks pretty good. So I'm going to turn off the vacuum. You can see the vacuum released a little bit there. And I'm going to go grab my watch glass. So we've got our watch glass here. And I'm going to move the filter and the aspirin to the watch glass. Now I weighed the watch glass because I think a lot of that aspirin is just going to fall onto the watch glass as I try to remove the filter. I've got a spatula here. I'm just going to run around the side of the filter to try to get the filter out of there. And see, I'm just going to dump it on there. Then get all the rest of the aspirin off. So that's why I weighed the watch glass, because I didn't think I was going to be able to get the filter out of there without making a mess with the aspirin. And I was right. So now we're going to let this dry. We'll let it dry overnight, and then we'll come back and weigh the watch glass with the filter and the aspirin on it. Alright, so I need to clean up that liquid that was filtered through. I know it's really acidic because it's got the sulfuric acid in it. So what I've got is a waste container. It's labeled as aspirin waste from the filtrate, and it says acidic on it. I just got this out of the hood, so I'm going to dump this solution in here, just so we can neutralize it and not dump it down the sink, because you can't dump acidic things down the sink. Okay. So now what we'll do is we'll rinse out our flask and our filter funnel. make sure they're all clean, and we'll be done until we have to weigh our sample tomorrow. All right, we're here at the balance. We've got our product here. It's dry. There's quite a bit of it. You can see it there. Remember, we weighed the filter paper and the watch glass separately, so we'll have to subtract those off of our total weight. So we need to do two things yet. We need to weigh our sample, and so we can get our percent yield, and then we need to test the purity of our product. So let's get our weight, and then we'll go test the purity. So the mass of the watch glass, the filter paper, and the aspirin at the end is 51.058 grams. So now we can figure out our percent yield. Remember, we need to subtract off the mass of the watch glass and the filter paper. So now we'll go test the purity of our product. All right, we're here to test the purity of our product. We've just got its mass. Now we want to see how pure it is. So what we're going to do is mix it with some iron 3 chloride. And the reason we're doing this is that iron 3, when it's in the presence of salicylic acid, or the salicylate ion, will form a purple complex. So if we just take some of our salicylic acid, some of that white powder that we started our reaction with, and mix some iron 3 in with it, you can see it's a violet colored solution. Alright, so that's, if I don't have any aspirin and it's all salicylic acid still, I get that kind of darkish, medium dark violet solution. Right? So what I want to do is take some of our product, and I'm going to add some water. It's not going to dissolve all that well. Aspirin doesn't dissolve in water all that well. I'm going to take a little bit of our product here and put it up here so you can see there's just a little bit of crystals in the bottom. And it tells me to add 5 milliliters of water. So I have my DI water here and a 10 milliliter volumetric. So you can see I've got 5 milliliters of water, and I'm going to add that to my test tube. So basically what we're testing for is if there's any salicylic acid left over. Did it all convert, or did we wash it all out, or is there still some mixed in there? Now remember, salicylic acid was the one that caused serious stomach problems. So we clearly don't want any of that in there. That's the reason we did this reaction to convert it to aspirin. So I'm just shaking it up a little bit here. And it doesn't have to all dissolve. Salicylic acid isn't all that soluble in water. All right. Now it tells us to add 10 drops of our iron 3 chloride solution. So I'm going to add 10 drops. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Put the cap back on here. Swirl it around a little bit. Okay, so I've got a white sheet here so we can kind of compare. So this is our solution. See, it's pretty clear. I don't see a whole lot of color in that at all. If we compare it to, this is a solution that's got 97.5% aspirin and 2.5% salicylic acid. So somebody ran a reaction and most of the material converted over to aspirin, but there was still a little bit of salicylic acid left in there. And you can see if we compare the two, that the one with the salicylic acid in, it's got quite a bit of violet color to it, and ours just does not. So if we compare it to 100% aspirin, meaning there's no salicylic acid in there, you can see ours is pretty similar. So we have a quite pure product. I'd say greater than 99%, probably nearing 100% pure aspirin. Well, at least not having any salicylic acid left in it. Right, so we've done the reaction with salicylic acid and acetic anhydride to form aspirin, acetylsalicylic acid, and we got a pretty good yield of the aspirin, and we've got a pretty pure product. All right, that's all we got. All right, so the last thing we need to do is get rid of our aspirin. I can't go down the sink, so what we have here is just a beaker that I'm going to scrape off the filter, get all the aspirin off the filter as much as I can, and then throw that in the trash. And I'm going to push the rest of our aspirin in there. We'll use it again for another experiment in a different class. Right, there we go. Just need to rinse off the watch glass and we're all done. All right, so see aspirin from CHEM111 lab, labeled beaker. And now we're all set.